Hello everyone, my name is Miguel. I'm the computer engineer for the Group 9 Senior Design Project for the Thermal Dune Energy Storage Battery.
And I'm Tanner Sear. I'm one of the electrical engineering students.
My name is Felipe Pestana Francis. I'm one of the computer engineering students.
My name is Michael Hernandez, and I'm the electrical engineering student.
So the Thermal Dune Energy Storage System is one that was made with the intention of being able to store heat during off-peak electric rates to allow users to save money over the long term. The two primary functions is that it's built around an ESP32 custom PCB as well as a DC to DC power supply. The user is going to be able to control it with a proprietary sort of LCD that we had built into the side here, which gives you the functionality of being able to control room heating as well as charging of the system. And I will let Lipe here talk about the LCD UI design.
So here's some functionalities that we created in the LCD. You can go to settings and you'll be able to set the charging time and the stop charging, the heating time, stop heating. Ambient temperature, it goes from 20 to 36 Celsius, or you can change the scale from Fahrenheit to Celsius. And you can save it and come back, you will see Celsius. Fahrenheit, sorry. I'm just gonna go back and save it again. This is the toggle for the charging. Turn on and off. For the heating, on and off. On. I'm just gonna let it run a little bit.
So the way that the overall system is made is so that it has one intake fan with a custom HVAC system inside of it, which will be able to control whether airflow can flow through the pipe or not. It does take a little while for the valve to fully open, which is why it also takes a little while for the fan to fully kick on. But when it does toggle, it will push air through some copper pipes that are embedded in the sand, and then we'll come to the output on the other side over here of the thermal storage system. So this will be your hot air outtake. The dimensions of the internal thermal storage is 2 cubic feet, so roughly about 150 pounds of sand, capable of storing up to roughly 8.5 kilowatt hours of energy. And now with this, you can't really see it, but I guess we could. You'll see it more in person. That hot air is finally able to exit the system. Lipe, if you want to go turn it off in the meantime. So one other thing that we wanted to implement with the system was mobile functionality. So with this, we built an overall app for the ESP32 that we have built into the overall system. It starts by creating a local access point. When it first turns on, it'll try to connect, and if it can't connect to a Wi-Fi network, it'll create its own little captive portal that you can connect to. And so you can connect to this with your iPhone, Android phone. It'll create a little splash page here that will show you the local networks that you can connect to. So in our case, we already have a test network here. I'll just put in the password. Galaxy 10 Plus. And when I press connect, the ESP32 will restart, and then it tries connecting to the network. When it successfully does connect to the network, you'll see a little Wi-Fi symbol that does pop up on that LCD there, and then we will start sending information to the web server. So with the web server, it does interface with our Thermal Dune Energy Storage app here, which I can log into right now. So we will log in, and then this will show me the information for the thermal storage device that is tied to my account. In the app, you do have the ability to add a thermal energy unit. In this case, for example, we already added it, but I would be able to give it a nickname as well as input the Thermal Dune Energy ID for it. So because I have it here already, we can see that the set room temperature will all match with the settings and everything. And in the profile, I can even set a custom a custom schedule for this that will be able to be used by the ESP32. So for example, if I want to set this to start charging at 16, I'll just do 16, let's do 30, let's do 33 here. When I press save schedule, it'll take the information that I had put into the app, save it to the web server, and the ESP32, which checks the web server every 15 seconds, will be able to get that information that I put in, and then hopefully be able to display it here when it receives that data, which should be, there we are, and then the information is updated. So now at about 16:33, about 15 seconds, you're going to see the little green light turn on and the overall battery will start charging. And I'll even hold this here so you can see it start charging as well as soon as we cross that 33-minute mark. That way I can ensure that the schedule worked correctly. And there you go, you see the light turned on and you see the power usage starting to increase for the Thermal Dune energy storage to start charging. And I'll hand over the information now to the electrical engineers in the group to start talking about the PCB.
Hi, my name is Michael Hernandez. I'm one of the electrical engineers that worked on this project.
And I'm Tanner Sear, the other electrical engineering student.
So for this project, our main responsibilities was to be in charge of the electronic hardware as well as the enclosure. And if you see here, the sandbox. So starting off with the electronic hardware, we have here our PCB box. But if you open her up, so we have two PCBs. The first PCB you see right here is our custom power supply. So as a power requirement, we wanted to take AC voltage in from a regular power outlet from an off-the-shelf AC to DC converter, which converts 120 volts AC to 24 volts DC. From this right here, it feeds into our custom PCB. This is feeding 24 volt input, outputting 3.3 volts, which is the optimal range for the ESP32 right here. Now the main board is the brains of this project. As you can see here, we have the ESP32 with a heat sink that's going to help dissipate all the heat that's coming in here. We also have all these connectors, JST connections, that relay out to the DHT11s, the thermocouples, and then as well as our relays down here. Now for our relays here, they're the ones that are in charge of providing power or shutting power off, depending on if we want to charge or heat. So going a little bit more into our main board, here we have our power protection unit. So this LED is letting us know that we're actually getting power to the board. This little circuit right here, we have two protection diodes. That way, whenever we apply power here, we ensure that we're not getting any kind of voltage towards our USB side. And speaking about the USB side, we have our programming interface here. This USB allows our computer engineers to connect via the Arduino IDE. That way they can program the ESP32. This feeds directly into our CP2102 bridge, which converts USB to UART. Going more into here, we have our LED display. So this was a major part here. Because we have digital lines, these are all high-speed lines because we're using SPI. So because of that, we wanted short traces from here to the ESP32. Okay. So those are the main components of the boards. And then as well as we have our sensors here right here. So like I said, we have our thermocouple sensors, which connect directly into the sandbox. This is taking the internal temperature and is reading it back to the LCD display. We also have our DHT11s outside of here. These DHT11s are reading the ambient temperature of the room. That way, the internal temperature of the computer knows to adjust accordingly. So once a user has set a desired temperature, the DHT11s take that temperature, compare it with what the temperature is outside, and if needed, it's going to start heating or stop heating. So those are the main components of the hardware. Speaking now about the enclosure and the actual sandbox, I'm going to pass it over to Tanner.
Thanks, Michael. Yeah, so for the airflow of this system, we decided to go with a 3-inch HVAC tubing for the input. And here you can see the fan that powers the air through the system. Next to it here is the valve that controls airflow. So when this valve is closed, the hot air remains inside the system away from other components like the PCB enclosure and the fan, which is greatly affected by high temperatures. So going from the 3-inch HVAC system inside the sand enclosure, we have two 5/8 inch copper tubes coming up around here and here in the sand enclosure. They actually are funneled into the system. The diameter is shrunk for both pipes, creating a high velocity and low pressure inside the box with a high pressure, low velocity in the HVAC system. This guarantees that the hot air will continue to move forward and will not have back pressure flowing backwards through the system. On top of the sand enclosure that we actually hand welded and crafted, along the insulation, we have the output of the copper tubes elbowing and coming here. We actually have a couple coiled here to soak up some of the extra heat from the enclosure to keep the air warm upon exiting the system. And here you may be able to see the two copper tubes coming through to exhaust the system with the hot air. Those are each, as I mentioned, 5/8 inch. So we have about like an inch of diameter in total coming out of the system. And I'm actually going to turn on the airflow, the heating, and give the valve about 15 to 20 seconds to fully rotate, and then the fan and the pump should push air through the system. While the air flow is off, temperature reading at the exhaust valve point is about 28 degrees Fahrenheit. I'm sorry, Celsius. And as you can see, it greatly increases on exiting once the airflow flows through the machine. Initially, the air is a little bit cooler just because of the stagnant air that was in the box and in the copper on the top of the box. However, as you can see, it still will increase as time goes on, and this will heat the room as specified. The sand enclosure itself, I know you can't see with the insulation, but it's actually a 2 by 1 by 1 cube. So running this way, it's 2 feet by 1 by 1. And we calculated that this amount of storage, the 2 cubic feet, allows us to maintain and hold or store about 8.1 or 8.2 kilowatts of heat energy. So essentially we created a 8 kilowatt heat battery. Here we have our terminal block. This controls or allows us to wire devices to the 120 volt coming in through this cable. We have a 24 to 12 volt DC converter. This runs from a relay that I will get to and show you in a moment. Runs from that relay to the valve bilge pump that we're using as a fan. Up here, you can see our 120 to 24 volt AC DC converter. From this converter, we supply power to our relays. First of which, here is an AC relay. So it's rated for 120, and that allows us to turn on and off the power going to the heating elements inside the insulated sand enclosure. The 2 relays here are both 24 volt DC relays. They power the valve